Question 10 is a really interesting question. So we start with a sequence u1, u2, u3 all the way up to u infinity, where u1 is equal to 1, and the next term is defined by the previous term minus this expression over here. And we have to use the first part wants us to use mathematical induction to prove that un is equal to this. So you guys should be quite pro at mathematical induction now. I think you know what you need to do. Let Pn be the statement, un is equal to 1 over n squared for all positive integers n. So positive integers n of course means integers n bigger than or equal to 1. So the first thing we want to do is prove the base case. So when n equals to 1, what do we have? Well, the left hand side of P1 is u1. u1 is equal to 1 by definition, and that is equal to 1 over 1 squared, which is equal to the right hand side of P1. So we've got left hand side of P1 equals to right hand side of P1, therefore P1 is true. So far so good. Now, after I've set up my definition, done my base case, need to set up my induction hypothesis. Assume pk is true for some positive integer k, i.e. that the sum, sorry, not the sum, i.e. doing too many sum questions, uk is equal to 1 over k squared. We want to show pk plus 1 is true. Right, so what do we do? Let me just scroll down a little bit. Okay, so what is the left-hand side of pk plus 1? Well, that's going to be uk plus 1. Easy enough, right? So what is uk plus 1? Remembering that I've got to get a uk to appear so that I can use my induction hypothesis. Fortunately, since I'm dealing with the recurrence relation, I can use the definition of the recurrence relation to say uk plus 1 is uk minus 2k plus 1 over k squared n plus 1, k plus 1 squared. And this is by definition of the recurrence relation. And this is fantastic because now I've got my uk and I can write that as 1 over k squared. And that's by my induction hypothesis. Right, so now I've done what I needed to do. I've used my induction hypothesis. It's just about simplifying it until the answer comes out. So I see that there's a 1 over k squared common to both, so I might just take that out. Actually no, I'm not going to do it that way. Yikes, what happened there? Holy holds, holy holds. Okay, hold on, there's something really wacky going on. Yes, really wacky. Okay. I'm going to make them the same denominator. That would have been a smarter thing to do. So I'd get k plus 1 squared minus 2k plus 1. Remember your brackets here, trap for young players, because too many people will write minus 2k plus 1. It's minus 2k, sorry, 2k plus 1, all in brackets. So this is actually a minus 1 here. K squared, k plus 1 squared. So what does that give me? Well, the top line will give me k squared plus 2k plus 1 minus 2k minus 1 over k squared k plus 1 squared. And you can see that the two k's will cancel, the 1 and minus 1 cancel, and so that leaves me with k squared over k squared k plus 1 squared. Look at that, those two cancel. I'm left with 1 over k plus 1 squared, which is equal to the right hand side of pk plus 1, which is fantastic. That's what I wanted. So therefore pk plus 1 is true. And what can I say? Well, therefore, since p1 is true and pk true implies pk plus 1 is true, therefore, by the principle of mathematical induction, Pn is true for all positive integers n. And that takes care of part 1. But of course we aren't finished. So we move on to part 2. Hence find this summation. So if you remember, we actually are told that un plus 1 is un minus 2n plus 1 over n squared n plus 1 squared. So if I'm going to find out what this is equal to, well, it's going to be the sum of the difference of my recurrence relation, right? So what does that mean I'm likely to be using? I'm probably going to be using method of differences here. So let's see what happens. I want the sum n equals 1 to capital N of 2n plus 1 over n squared n plus 1 squared. What's this equal to? This is equal to the sum n equals 1 to capital N of un minus un plus 1. So that this number, the positive of it, would be un minus un plus 1. Well, what am I going to do now? I'm just going to try a few values of n. So if n equals to 1, I get u1 minus u2. N equals to 2, I get u2 minus u3. N equals to 3, I get u3 minus u4. You can kind of see the pattern, right? What about the last two lines? I get un minus 1 minus un plus un minus un plus 1. So this is definitely method of differences. What cancels out? Well, you can see the u2's cancel, the u3's, then something will cancel the u4, blah, 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 blah. Un minus 1 will cancel, un's cancel. I'm just left with these two terms. So this whole thing is nothing more than u1 minus un plus 1. And thanks to our proof by induction in the earlier part, we know that this is 1 over 1 squared minus 1 over n plus 1 squared. This is just 1 minus 1 over n plus 1 squared. So that's, again, not too bad. Give a reason why the series in part 2 is convergent and state the sum to infinity. So what are we going to do? Well, let's just look at it. What would the limit as n goes to infinity of the sum to n equals to 1 of 2n plus 1 over n squared n plus 1 squared b? Well, that would still be the limit as n goes to infinity of 1 minus 1 over n plus 1 squared, which is what we found out from the previous part. And so we know the limit of 1 doesn't change, is 1. But what happens as you go 1 over a bigger and bigger number? 1 over a million, 1 over a billion, 1 over a trillion. That 1 over thing just gets very, very, very small, and this approaches 0. So the limit is 1, and it exists because 1 over n plus 1 squared goes to 0 as n goes to infinity. So therefore, it is convergent, and the sum to infinity will be 1. The last part for this question asks us to use our answer of part 2 to find out something about this sum. So it shouldn't be too bad for you guys, because you can see it's very, very close to what we had before. It's just that this is a minus instead of a plus, this is a minus instead of a plus, and I've got this annoying 2 out the front. So what can I, but again, actually that's not an annoying 2 out the front, that's completely necessary. I need that 2 there. What am I talking about? So is there anything I can do to try and get this back to a positive? And all I need to do is I need to think about what should I swap in place of n to get positive numbers again. And I think you can see if I let n equal to r plus 1, then I would get back something that looked a lot similar to what I started with. Maybe I'll do this instead of just talking about it. So I've got the sum from n equals to 2 to n of 2n minus 1 over n squared n minus 1 squared. I use this substitution. I instead want to have the summation from, this will be from, every time I see an n, I'm going to write r plus 1. So from r plus 1 equals to 2, and implicitly in here, it's never written, but this is r, this is always n equals to capital N. So the top line will be n minus 1 now instead of n of 2, sorry, it stays as, yeah, of 2, and then I see an n, so I write r plus 1 minus 1 over, I see an n squared, so I write r plus 1 squared, n minus 1, that's just going to be r squared. And so now we recognize what this is. So this is just the sum. I can make r the subject, r from 1 to n minus 1 of 2r plus 1 over r squared, r plus 1 squared. And that is just going to be the sum of 1 minus 1 over n minus 1. Sorry, n minus 1 plus 1, so n. Sum of 1 minus 1 over n squared from part 2. And therefore we are complete.